Let's now turn to problems 20 and 21, making rough hand-draw sketchings of the following functions, stating the domain and range of each. Let's start off with the left column, just kind of go down. So x squared, the graph of x squared will go like this. And for this, the domain will be all real numbers, while the range will just simply be the positive real numbers and 0. So that's the domain and the range of x squared. This is going to be most related to the graph of, that's the x squared. This will be most related to the graph of x to the 1/2. The graph of x to the 1/2 is going to go like this. And so for x to the 1/2, the domain will be positive real numbers, or non-negative real numbers. And the range will also be non-negative real numbers. Okay. All right, these graphs are related by the transformation that x squared and x to the 1/2 are inverse functions. If x squared, we restrict the domain to the non-negative real numbers. So they are related to each other because the two graphs will be the reflection of each other through the line y equals x. So the two lines here are related. They are related by flipping across y equals x, and the reason this happens is because x squared and x to the 1/2 are inverse functions. So that's part of the problem. Let's now move on to another graph. So I'm going to start eliminating ones that we've already discussed. Let's now take a look at x to the 3/2. The graph of x to the 3/2, well, let's think about this. You have to have x positive, or at least non-negative, for this to make sense. So the graph of this is going to be somewhere between the graph of x and the graph of x squared. So that would be the sketch of the graph of x to the 3/2, where the domain is, let me write it like this, x greater than or equal to 0. And the range will be y greater than or equal to 0. So I could write the domain and range like this, or else using the set notation that I did in the previous example. So that is the graph of x to the 3/2. We cannot input a negative number because a negative number to the 1/2 does not return a real number, so that's not permissible. So let's continue on with some other positive exponents. Let's now take a look at x to the 2/3. X to the 2/3, it is perfectly permissible to plug in a negative exponent, or negative bit number. Negative number to the 1/3 power is perfectly well defined. So the graph of this is going to be something between x and the graph of x to the 1/2. So it's going to go something like this, where this is supposed to be symmetric about the y-axis. So the domain is going to be all real numbers, while the range will be y-coordinates that are greater than or equal to 0. So that's the graph of x to the 2/3. It's defined on both sides of the y-axis because I have a odd number in the in the denominator of the exponent. Let's take one more positive base, x to the pi. So x to the pi, that's x to the 3.14, etc. I have an irrational exponent, and so this will only be defined for positive values of x. So the graph of x to the pi will go something like this. The domain will be x greater than or equal to 0, and the range will be y greater than or equal to 0. In general, you cannot have a negative number to an irrational base. So that is the domain and range of x to the pi. Okay, let's now take a look at x to some negative exponents. First off, x to the -2. The graph of x to the -2 is going to kind of go like this, because it's 1 over x squared. X squared has to be positive, or at least not negative, and so 1 over x squared, if it's defined, has to be positive. So the domain is going to be x not equal to 0. Can't do it at 0. And the range will be that y has to be greater than 0. So that's that one. X to the negative 3. For x to the negative 3, we have a graph that will look like this, where it kind of goes like this, and same thing on the other side. It's not a hyperbola. 1 over x would be a hyperbola, but kind of has the same general shape. So for this one, the domain would be that x is not equal to 0, and the range would be that y is not equal to 0. Okay, x to the minus 3 halves. This is only going to be defined if x is positive, because I have an even number in the denominator of the exponent. So x to the minus 3 halves will go something like this. That's 1 over x to the 3 halves. And I can't have a negative number to the 3 halves power. So the domain for this will be x is greater than 0. And the range will be that y is greater than 0. Let's now take a look at x to the negative 7/5. So for this one, we have 1 over x to the 7/5 power. So this is perfectly well defined if x is negative, because I have a 5 on the denominator of the exponent. If I raise a negative number to the 1/5 power, that's negative. If I take that to the 7th power, that's also negative. So the graph of x to the negative 7/5 will have this general shape. And so the domain will be that x is not equal to 0, and the range will be that y is not equal to 0. Okay, let's now turn to the exponential and logarithmic functions that we have. Let's take a look at, in turn, let's take a look at 2 to the x, 0.5 to the x, log of x base 2, and log of x base 1/2. Okay, and I'll probably change the color coding on this as we go along. The graph of x 2 to the x will go like this. So that's the graph of 2 to the x. So the domain is going to be all real numbers, while the range will be that y has to be greater than 0. One way of get a common graph will be the log of x base 2 function. So let me plot that one in red. So log of x, 2 to the x and log of x are inverse functions. And so the graph of log of x will go something like this, where the graph is going to be a mirror image through the line y is equal to x. So the domain of this function will be the flip of what I had before, x greater than 0. So here the range was all positive real numbers. Here the domain will be all positive real numbers. The range of this function, well, the previous domain was the all real numbers, and so the range of this function will be all real numbers. So that's the properties of the logarithmic function, and this happens, there's an algebraic relationship because 2 to the x and log of x base 2 are inverse functions. Okay, let's now take a look at another possible transformation. So let me get these out of the way. Another possible transformation is going to be 0.5 to the x. So let's draw this one in green, 0.5 to the x. And notice that 0.5 to the x is equal to 1/2 to the x, and by the laws of exponents, that's equal to 2 to the minus 1 to the x, which is equal to 2 to the minus x. So notice that 0.5 to the x is the same thing as 2 to the minus x. So that means I can take this graph 2 to the x. If x gets replaced by minus x, then the graph of 0.5 to the x is obtained by just simply flipping through the y-axis. So if I take the graph in black and flip it carefully through the y-axis, so this part in green matches this part in black, this part in black flips over to get this part in green. So the green graph will be the graph of 0.5 to the x. And it's an exponential function, so the domain, as before, will be all real numbers, and the range will be y greater than 0. Okay, finally, we can now draw the graph of logarithm of x base 1/2. So let me plot that in brown. And to obtain this function, I would take this green curve and again flip through the line y equals x. So let me do this really carefully. So if I have this diagonal line, y equals x, the curve in red is the flip of the curve in black. Then I need to take the curve in green and flip across the purple line. And so I would have a part that goes up this way, and also a part that goes down this way. So the curve in brown is the graph of logarithm of x base 1/2. The domain will be all values of x that are greater than 0. And the range will be, again, all real numbers, flipping the roles of domain and range in the home function in green. Notice that the curve in red is also the flip of the curve in brown across the x-axis. The reason that happens, let me clear this out. So the reason that happens is because the logarithm of x base 1/2 is equal to the logarithm of x base 2 divided by the logarithm of 1/2 base 2. And the logarithm of a half base 2 is -1. So the bottom here is -1. So the logarithm of x base 1/2 is the same thing as negative log of x base 2. So that goes to show that the curve in red and the curve in brown are mirror images across the x-axis in the same way that the curve in green and the curve in black are mirror images across the y-axis. Okay, so that's part of number 20. Let me clear off what we've already done. So we've done that, we've done this part, and we've also done these two parts. Okay, so let's now take a look at the graphs of 10 to the x and 0.1 to the x. The graph of 10 to the x goes like this. It'll be a lot steeper. That was a bad picture. It'll be a lot steeper than the graph of 2 to the x that we had. And the graph of 0.1 to the x, I'll let you verify by the same logic we had before, is the same as the graph of 10 to the minus x. So the graph of 0.1 to the x will go like this. Exponential decay going positive as opposed to exponential growth. And for both of these, the domain is all real numbers, and the range is y greater than 0. Okay, that takes us to our final set of functions. E to the x, e to the minus x, and natural log x. This will be very similar to the graph that we had before for when 2 was the base as opposed to e. The graph of e, so I'll do this in black, the graph of e to the x will go like this. The graph of e to the minus x will be the flip of that picture over the y-axis. So there's the graph of e to the minus x. And for both of these, the domain is all real numbers, and the range will be all numbers greater than 0. Finally, we need to get the graph of natural log x. Well, e to the x and natural log x are inverse functions, and so if I have the line y equals x, the graph of natural log x will be the flip across that green dotted line. And so for natural log x, the domain will be all positive real numbers, while the range will be all real numbers. And the reason that happens is because e to the x and natural log x are inverse functions.